In this lecture, we will learn about the virtual memory, particularly what is virtual memory and what are the issues that virtual memory can handle. So we will learn about what is virtual memory and how to implement or map the virtual memory. So I would like to start with two questions that I have asked you in the last classes. The first thing is, does a computer can work only a single task at a time? The answer is straightaway no, because we are using the Internet Explorer or browser, and at the same time we are using writing program in running by another compiler. We are watching videos and many other things in the computer. So multiple program running in the computer at a time. And the second question is, once you run all the multiple program, the size of all the program together is bigger than your RAM. What happened? So we can know that all of our memory interaction instruction in MIPS, that means the load word, store word, that try to find out the data in a memory address from the RAM. But what happened if the size of the RAM is smaller than the program you are executing? Once you think about the virtual memory, you have to keep in mind these two questions, and the virtual memory particularly serve answer of these two questions. So for example, a computer with only 128 megabyte of DRAM, primary memory, for example, could effectively provide even though 2 gigabyte of memory using the hard disk. So this larger 2 gigabyte memory is called the virtual memory, and the smaller 128 megabyte main memory is called the physical memory. What I want to explain here, if your program is greater than your RAM, the extended part is basically the virtual memory. So we can conclude, as all of you studied the cache memory, which is a copy of physical memory, and in case of the virtual memory, we can say that the physical memory holds a subset of the most recently accessed virtual memory. In this way, the physical memory acts as a cache for the virtual memory. Again, the question is, if we don't have enough memory, what happens, right? So as all of you know, the MIPS address is 32-bit. So the load word or stored word instruction specify a 32-bit address, right? That we have studied during the assembly programming and also during the microarchitecture. So thus the MIPS program can access any byte in a 32-bit address. And what does a 32-bit address mean? A 32-bit address is a space with the range from 0 to 2 to the power 32 bytes or 4 gigabyte. So we are discussing about the MIPS instruction that promise to access any location within the 4 gigabyte, but if we don't have 4 gigabyte memory, what happens? The answer is handled by the virtual memory, right? So before discussing the solution, let's have a look about some issues that cannot be handled without the virtual memory. So the first thing is, if we don't have enough memory, what happens? So here is a program size of 4 gigabyte with address 00 to this. This is the 4 gigabyte of address. Now you have a 1 gigabyte of RAM with 30-bit address. So as I have discussed in the classes during studying cache, the memory is like this. The first part of this program is mapped with the RAM like this. And similarly, the second part and third part is like this. And as the program contains the remaining part is not possible to load in the RAM, so your program will be crashed. So this is the limitation. So you must have to have 4 GB of memory. Even if you don't have the 4 GB memory, the program cannot be executed because this program line is not finding in your RAM. Well, this is the first issue. The second issue is when you run the multiple program that share the memory. So you have, for example, 32-bit addressable 4 GB of RAM, and you're running 3 programs, different programs. For example, this is Internet Explorer with 1 GB memory, and this is word processor taking 2 GB, and this is another program you are watching a video game having the 4 GB program. Okay, so you want to run this for 3 programs simultaneously. Well, the first program is occupied the 1 GB of the memory address like this. This program is loaded here and run to execute it. At the same time, the second program is executed here. I want to run the third program is gigabyte having the 4 GB, but we have remain only 1 GB of space. So this program, when you run the program, it crash and it is not possible to solve. So the first thing is, again go to the slide. If we don't have enough memory, the program will not crash. If we have the program, multiple program, the remaining program cannot be handled. It's the same reason for the multiple program, right? And the number 3 is, well, you have the space. Like consider this scenario, we have the program 1 occupied this, but program 1 quit. So this memory address 1 GB is now available, but the program 2 is still executing, so they occupied this location, and then here we have another 2 GB, 1 GB here. So this program 3 having 2 GB of content, we also have 2 GB available in the memory, but not in a single row. So it's supposed to be run with this, but there is no way to segment this program into the first gigabyte and the second gigabyte like this. So it is not possible to handle, even though you have the memory space. And the last but not least is a very important and severe issue, a security issue that cannot be handled. Is called the memory override. For example, you have one program that using the store word R2 1024R0. The value of R2 and R0 remains same during the execution. And for example, this is the memory address of this. Well, at the same time, program 2 also execute the same instruction. It could happen. And for example, the program 1 stored my student ID in this location, while program 2 stored the name in the same location. So what happened? Well, program 1 executed earlier than program 2. It's gonna store your student ID here, but after some time it's replaced by your name. When your program 1 again call from this location for the student ID, he will receive the student name. So this is a severe problem called the memory override. So it cannot be handled without the virtual memory. Now let's sum all together. If you don't have enough memory, if you have the memory but we have running multiple programs, and we cannot handle the memory fragmentation. That means we have the available space in our memory but not at a row. That means we cannot fragment our program to load it into the memory even though we have the memory available. And the last thing is override. The multiple program can execute the same instruction to write or read from the memory. Well, so the virtual memory is answer of all the issues. So I write down all issue, one solution. So using the virtual memory, we can solve all the issues. Well, then let's have a discussion how we can solve the 4 issues in here. So this is number 1, if we don't have enough memory. Okay, so as I said, that in that case we need to use our virtual memory is here and we have a map. So with the virtual memory, this is the typical diagram. So we need to add a map. So our program here is like 4 GB of memory, but we have RAM of 1 GB, and these are the remaining part are the virtual memory in our hard disk. So the first part, program loads the address 0. This is the program line, and it maps the RAM. This is the program 0 in the RAM position 1. For the program line 1 in the program, it maps in the RAM the position 0. Well, the program executing. Well, the program address load address 2, it maps to the program RAM address 2, to 0, 1, 2. And what about the next one? That means, so when the program loads address 3 in this program, now it is loaded to the hard disk. That means the virtual memory. Well, now what I have to do, the program 3 is here. So what we have to do, we have to change someone from here and load the program 3 here. For example, the program 0 is come here, and then program 3 is copied here in the 1 position of the RAM, and then we need to update the memory. The program 0 is now gone to hard disk, while the program 3 is now mapped to the second position of the RAM. Well, now move to the second and third, the memory fragmentation. As you know that we have 2 programs. So the one program is running here and another program is to be executed having 2 GB of memory. We have 2 GB memory in the top, 1 GB and the bottom 1 GB. So how the virtual memory can solve? So we need to use 2 map for this position. So we are segmented the first map here, 1 GB from the program 2, and the map 3 that maps the another 1 GB for the program 2 like this way. So the mapping should be this way. So the solution is each program having its own mapping. Well, so in that case, if each program having its own mapping, and then it can be used this way. And the last but not the least is memory override. Here also multiple access the same address. How can we solve it? The program containing each program having the different each own mapping. So while the program 1 executing the instruction store word, it mapped to this position. At the same time, this map handle, while the map 1 using this map 2 will never use this. So the same instruction map 2, my name is stored in another position for the memory. So never possible to conflict. Well, these are the solution of all the issues, and the solution is by the virtual memory. Well, in this lecture, we will use the term map. Map with the program, that means the mapping with the program and the main memory with the virtual memory. So we know that all the issues from issues 1 to issues 3, 4 solved with the map. So the next part of this lecture, I mean video 2, we will learn about the mapping. And this is all about the first part, virtual memory. So we learn how we can solve the issues of memory access by the virtual memory.